All right. Good morning, everybody. I know this is a good almost evening for me on Sunday, the 3rd. You should be watching this on the 4th at 9 a.m. At least that's when the video will go live. I do apologize that we've come back to this recording setting. I really wish that this had not happened, but due to an unforeseen set of circumstances due to my health, which, by the way, I'm okay right now. I'm healthy, at least for now. I was admitted to the hospital last week on Wednesday morning, and I was finally released from the hospital on Saturday. Uh, the cause for why I was in the hospital turned out to be something that I was not expecting. It is a specific medical issue that could turn for the worst, but at the moment, knock on wood, things are okay. But because I'm still kind of in that recovery phase right now, I honestly barely have the strength to record this, but y'all have to learn, right? Due to the fact that I'm still recovering at the moment, I will be teaching this class on through an asynchronous recording format, which is how you're seeing it right now. Give me 1 second. My dog is doing something he's not supposed to do. Sammy, what are you doing? Why don't you go to the couch? Why don't you go to the couch? Yeah, you're adorable, aren't you? So, I did make an announcement earlier on Sunday with regards to changes that have to be made due to the fact that I was not present on Wednesday last week and Thursday's lab session because I was in the hospital. I do want to talk a little bit about that right now. So, before we get into the brunt of our material here, let me insert a page here. I'm going to kind of summarize the information that was released on the Sunday announcement. So let me pull that announcement up on my desktop here, which is right next to me. So let's go here for just a moment. So obviously this lecture is going to be It has been recorded for the Monday lecture. At the moment, I do plan to return to teach in person on Tuesday. So Tuesday lab, I should be there to administer the lab practical. So that has not changed. Wednesday lecture should be in person. So expect Dr. O will return to campus on Tuesday. So that hopefully nothing changes from that. Again, at the moment, I'm okay in terms of my health, but things could turn from what my doctor explained to me. If I see a certain set of things happen, then I have to go back to the emergency room. Let's hope that that doesn't happen, though. With regards to our discussion, the Monday discussion will be canceled. So what I'm going to do here is I'm going to go to the calendar here. Let's go all the way down to our very last week. So the Monday discussion that is the very last week that takes place on the 4th will be canceled. The Wednesday discussion, which will take place on the 6th, will be scheduled as normal. Now, the reasoning behind this is last week on Monday we had discussion, but on Wednesday I got administered to the hospital, which means I wasn't there. So to kind of keep things balanced out, I'm going to cancel the Monday discussion, but keep the Wednesday discussion so that I'm able to not drop as many assignments as I want to. Now on Wednesday's lecture, I will show up and hand out the last two discussion worksheets for all students because obviously last week on Wednesday, students who were in the Wednesday discussion were not administered the Vesper worksheet. So I'm going to give you that. And this week, the Monday people would not have seen the molecular orbital diagram worksheet. So I will be providing that for your use in studying for the final exam. So I'm going to write that to Monday. Oops. Monday 12 for discussion canceled. All right. Let's talk about. I have a list of things here that I want to talk about. First off, because we are, as you're watching this, we are now 1 week away from the final exam. I do want to talk about the final exam. So let's kind of cover for just a little bit final exam info. So the final exam is scheduled, if we look at our calendar here, is scheduled for Monday, December 11th from 8 a.m. to 10 a.m. So final exam is, let me go back here again, December 11th. December 11th from 8 to 10 a.m. If you have accommodations, please be sure to schedule with the testing center ahead of time so that they can get you your accommodated time, whether that's 100% extra time, 50% extra time, whatever that may be. If you have a scheduling conflict, that's something that is going to come up for the final exam, then please let me know as soon as possible so that we can schedule something either very late this week or some other time on the finals week, later in the week. I would prefer late this week if we have to reschedule your final exam, simply because I am going to try to get grades out as soon as possible. Not only because I want to get grades out as soon as possible and begin my Christmas break, but also because due to this medical emergency that just happened, I will probably be seeing some doctors in the coming days. So again, be on the lookout for some Canvas announcements in case there are additional changes, because I may have to see a doctor later this week, specifically a hematologist, which is a doctor of blood. I don't want to divulge too much information, but I will say this. As far as I know, and my doctors that did scans while I was in the hospital, it is not cancer, which I'm very, very grateful for. But there are a few tests that are still being processed that I'm waiting for information that I will be talking to the hematologist about. Okay, so final exam is scheduled for December 11th from 8 a.m. to 10 a.m. Again, if you have accommodations, please schedule with the testing center. And if we have to reschedule your exam, please get a hold of me as soon as possible. I will try to get back to you as soon as I'm able to. In terms of the practice final exam, there is a practice final exam posted on Canvas. And on Wednesday, because I will be hopefully returning to teaching classes on Wednesday, I will be able to provide you with the printout of the practice final exam. Let me make sure that we're still recording here. Okay, I am recording. And how long have I been recording for? Let's see, about 8 minutes. Okay, that's fine. All right. So the practice final exam, along with its key, will have been posted. Now, the final exam is a little bit different in terms of what I can give you to practice, to study for the exam. The final exam is to a certain extent standardized among all other Chem 400 professors here at SEC. Now, that means that unlike the previous midterms where I provide you the first page of the exam that tells you how many questions there are, how many points the final exam is worth, what the free response questions are going to cover, I will not be providing that for you for the final exam. The equation sheet will be provided for you. In fact, the equation sheet is exactly the same equation sheet that's going to be on the practice final exam. So if you're wondering what equations you don't have to memorize, what specific constants you don't have to memorize, that will be given to you on the practice final exam. You just go to the last couple of pages. Those pages are going to be exactly the same as you would expect it on the final exam. In fact, all the equations that you've received for the previous 3 midterms on the equations page should be on the final exam. And if there's one that I missed, I will provide it for you during the final exam. I did take the time to sit down and make sure that all of them have been accounted for. But the first page will not be provided for you, which means you have to take the final exam essentially blind. Now, I can give you this information. Final exam will cover all material from class. This is sections 1 through 9. I know I'm not including 10 here. I'm going to talk about section 10 in a little bit after I'm done talking about the final exam. It is more common for my final exam specifically to weigh a little bit more on topics that have not been tested on yet. So up to this point in class, midterms 1 through 3 have covered sections 1 all the way up to section 7, which is periodic table, periodic trends. The final exam will have a little bit more. It's going to weigh a little bit heavier on questions that have not been tested, which is going to be sections 8 and 9. This covers bonding 1 and bonding 2. So expect the final exam to have more questions with regards to Lewis structures, molecular orbital theory, hybridization, Vesper theory, dipoles, that kind of topic. There will be questions from previous sections, and in fact, I think I made a joke about our first midterm that said that, hey, a lot of people did really poorly on that combustion analysis question from the very first midterm. It's going to show up on the final exam. That question is going to show up on the final exam. I would also like to point out that specifically the Hess's law question from midterm 3, a lot of people did very poorly on that question as well, which means that one will also show up on the final exam. Those are the only 2 tips I can give you. I cannot give you any more than that because, again, the final exam is standardized to a certain extent. The last thing that I want to talk about for the final exam is because the final exam is standardized, it will not be returned to you at the end of the semester. So you'll take the final exam, you'll turn it in, I will grade it, the grade will show up on the Canvas site, and you will not receive your actual final exam that you took because the fact that the exam is somewhat standardized, we like to reuse some of those questions for future classes. So once I've graded all of the final exams and I've confirmed and double checked that the score is correct, I'm going to take the final exams home with me, and sometime over Christmas break, I'm going to shred them. They will all be shredded. They will not be returned to you because of this standardization. So that's all I'm going to talk about for the final exam. Again, if you have some questions with regards to the final exam, you could email me, you can ask me, but that's as much as I'm going to talk about. Now, I want to take a moment to talk a little bit about the fact that we missed lecture last week on Wednesday. So I was out on Wednesday and Thursday, so we did not have lab last week Thursday for the Thursday peeps, and Wednesday discussion and lecture were completely canceled because I was in the hospital. Due to the fact that we lost about 80 minutes worth of time, it means that we probably are not going to have, in fact, I don't want to say probably, we will not have enough time to complete section 10 at all. Because of this, I am dropping section 10 completely from the lecture material, homework material, and the final exam. So I'm just going to write down a little star. Section 10, which is properties of liquids and solutions. Dropped from class. I am very, very sorry that I had to do this. This was a very difficult decision that I had to make, but just given the circumstances, there's just not going to be enough time to cover it. The silver lining to this, besides the fact that you don't have to do that homework assignment, is The material for Section 10 is to a certain extent supplementary. A lot of the material you learn in that section, you don't necessarily require it for future chemistry courses. There's discussion. The only part that I would say is important for Section 10 is, I would say, intermolecular forces, but that is something that can be taught very. You can learn that very, very easily by reading the material, and it is something that will come up in organic chemistry if you're going to take OChem. But due to the fact that we just do not have enough time, I will not be covering that material. But it is available for you in the textbook if you want to read up on it. It is a fairly simple idea to cover, since you do since I have taught the idea of net dipole moments and whether a molecule is polar or nonpolar. That material does extend out into that topic. So the homework, lecture, and the final exam will not have any Section 10 questions at all. Like, we're completely dropping it. The Section 9 homework was supposed to be due, actually, I believe, today at 11:59. And while I'm recording this, because today is Sunday, I know you're going to be watching this on Monday morning, I have pushed back Section 9 homework. So Section 9 homework is due on Saturday, I believe, December, let me check my calendar really quick, December 9th, so 12/9 at 11:59 p.m. So I've dropped Section 10 homework, and because we haven't completed Section 9, I've just pushed back that material to be due on Saturday. Finally, the last thing that I want to talk about, a quick summary, is with regards to Experiment 9. Experiment 9, which was the analysis of the antacids, I was not there last Thursday. That means that any questions with regards to part 2 of that experiment do not have to be completed for the post lab. In fact, I'm dropping any question with regards to part 2 of experiment 9, so you don't have to worry about that. I do want to point out that the statistical analysis that you were supposed to complete required students to complete part 2, and because the Thursday lab didn't do it, you won't have to answer those specific questions on the post lab. This is also true for Tuesday people. So Tuesday people, you don't have to do that. I do want to point out, though, that because I did cover that statistical analysis workshop on Wednesday of that discussion, not Wednesday, it was the Wednesday before. I did cover, this was right after your third midterm, right before Thanksgiving break. Since I did cover that material, though that specific question may show up on the practical. So it is something that is technically still fair game, because I did cover how to answer questions like that during our discussion. But any question that shows up on the practical that's with regards to part 2 of Experiment 9, if it does show up, I will drop it. So you don't have to worry about that. With that being said, let's get started on Section 9 material here, because I just spent like 10 minutes, actually like 20 minutes, covering announcements due to my medical emergency here. I know I have this extra credit question for XEOF4. I'm going to leave that for Wednesday. That's going to be the last extra credit question for the semester, because we're not in person during this discussion. So let's see what we're going to talk about today. So last week on Wednesday, we talked about, or last week on Monday, sorry, because Wednesday I was not here. We had a discussion about how bonds are formed. If two hydrogen atoms are allowed to come together so that their atomic orbitals are allowed to overlap, we observe a bond that is made at a specific point where the potential energy of the bond is at its minimum point. And so the radius between the two nuclei for the hydrogen atom is about 74 picometers. Of course, I can't make these atoms any closer to each other, because we have the nuclei are going to start to repel each other. Now, what we're going to observe in this section is when two atomic orbitals come together to make a bond, it's going to create a new set of orbitals. Whenever you make a bond between two atoms, you create what we call a molecular orbital. And due to the fact of the law of conservation of mass and energy, which is the very first thing we covered at the very beginning of the semester, when I make a molecular orbital, so if I take two atomic orbitals and I make a molecular orbital, I begin with two atomic orbitals, or however many I begin with, and I end with one molecular orbital. Well, something isn't adding up here, because if I start with two and I have the law of conservation of mass and energy that I have to obey, I should end with an equivalent two molecular orbitals. Well, what ends up happening is when I create a bond, the actual mechanics of the creation of that bond cover two types of molecular orbitals. We have a bonding molecular orbital that's made, and what we call an anti-bonding molecular orbital, which is the literal opposite of a bond. So on the next page, we see what happens when two atomic orbitals, here we have a diagram showing the molecular orbital that is formed when two 1s orbitals for two hydrogen atoms are allowed to combine with one another. So what we see here is the two atomic orbitals combine together. The wave function for these individual atomic orbitals combine to make this large oblong molecular orbital, which is a bonding orbital. And we're going to signify this bonding orbital with the Greek letter sigma. Sigma signifies the bonding orbital that is created from individual atomic orbitals when they come together end on end, such that there is no nodes that bisect the nuclei. So these little dark blue dots that you see here are the nuclei for the individual hydrogen atoms. And there is no way I can draw a dashed line between the two nuclei that corresponds to a node. So the definition of nodes are still going to extend here from atomic orbitals to molecular orbitals. So we're just going to signify with the Greek letter sigma. The 1s corresponds, it tells the reader that this molecular orbital was formed from two 1s orbitals. And you notice that the overall energy of the molecular orbital is lower overall than what we started with. And that's why we want to make a bond, because again, it takes the energy of the electrons and places it in a lower energy state. Now, the opposite of that is going to be an anti-bonding orbital. An anti-bonding orbital happens when I take the two corresponding atomic orbitals and I try to add them together, but instead of making a molecular orbital that goes all the way through, that connects the two nuclei together, I create a molecular orbital that has a node that separates the two nuclei from one another. This is still technically a sigma bond, but we call it a sigma star. The star, wherever you see it, and we're going to see it more than once here. Let me use orange here. The star always corresponds to an antibond of some type. Whether it's a sigma antibond, we're going to learn about pi bonds. You can have a pi star bond, which is the antibond equivalent of a pi bond. And you'll notice that the energy equivalence of this bond, which isn't really a bond, it's the opposite of a bond, is higher in energy than what I began with from my two atomic orbitals. So it's a molecular orbital that is higher in energy than any of the atomic orbitals from which it was formed. The asterisk in the notation signifies that atomic that antibond. So in general, what we're seeing here is the definition of constructive and destructive interference. If my two atomic orbitals are in phase with one another and they were to add to one another, then they create a molecular orbital, as shown in this oblong shape at the bottom. So this is a sigma bond that is formed from a 1s orbital pair. But if they are opposites, then they subtract from one another, which means they are out of phase. This creates an antibond. So if they are in phase, we have constructive interference. They're allowed to add to one another. We make this molecular orbital that is bonding in character. If they are out of phase, we have destructive interference that is out of phase with one another, you make an antibond. Now, the general purpose of this idea of molecular orbital theory is it will allow us to quantify exactly the amount of energy that can be stored inside of a bond between two atoms. We can have a central atom that bonds more than two atoms. Obviously, we can go all the way up to an octahedral molecule. Now, for this section of class, we're only going to cover diatomics. This is going to be linear molecules, and it's because the general outline to make a molecular orbital diagram, which we're going to see in a little bit, for any type of geometric structure that is more complex than a linear molecule requires a linear algebra. It requires linear algebra, and it requires an understanding of the geometry of these molecular orbitals. It's beyond the scope of the class. It's too complicated. So this is as far as we're going to go. But when we combine any number of atomic orbitals to make these molecular orbitals, whether it's a bonding MO or an anti-bonding MO, this is what we call the linear combination of atomic orbitals, which is a fancy way of saying we're adding atomic orbitals to one another to make a molecular orbital, or subtracting them from one another to make an anti-bonding orbital. The linear combination of atomic orbitals is signified as the LCOW, or LCHOW. That's just the abbreviation for it. Again, it's just the weighted sum of the atomic orbital to make either a sigma bond, which is the resulting bond that forms between two s or two p orbitals, or hybridized orbitals, which we'll talk about in a little bit, in which the overlap is end on end. It is important that they're end on end because there are, again, no nodes. Let me use a blue marker here. There are no nodes between the atoms, between the nuclei of the atoms. So let's say nuclei of atoms. The other type of bond that we're going to cover is a pi bond. A pi bond is a bond that forms between two p orbitals that overlap side to side. This will have one node between two atoms that bisects the nucleus. So what will this look like? Again, we have our descriptor here of what happens when I take my two s orbitals and I allow them to either add to one another to make the bonding MO. So here's our bonding MO. Or they subtract with one another to make the anti-bonding MO. I can make a sigma bond with a p orbital set, though. Remember that p orbitals are like dumbbells, right? If I take two p orbitals and I line them up so that they're end on end with one another, where one p orbital comes from one atom and then the other p orbital comes from a different atom, and I allow them to add to one another, then I can either make a bonding MO where they add to one another to make the bonding MO that's described at the bottom of this diagram, that's this thing, or I make an anti-bonding MO in which they are out of phase and they subtract one another. You'll notice that for the anti-bonding MO, regardless of whether it's a sigma bond or a pi bond, which we'll see in a little bit, is going to have this node that separates the two atoms from one another. A bonding MO does not have that node that separates the two atoms from one another. A pi bond happens when I take two p orbitals, and they have to be p orbitals, and they are allowed to overlap with one another, but instead of being end on end with one another, they're parallel to each other. What does that look like? Let's imagine I have two p sub z orbitals. So this corresponds to two atoms, and they're parallel to one another. If we have an in-phase p orbital set, then they'll add to one another to make a shape that looks like this. This is a pi bond that comes from two p orbitals. And this is a pi bond because if I go back to the definition for just a second, a pi bond forms between two p orbitals that overlap side to side. It has one node between the two, let's say the two atoms that bisects the nucleus. It's important. Two atoms that bisects the nucleus. If I go back to my diagram, Regardless of whether it's a bonding MO or an anti-bonding MO, there is a node that crosses the two nuclei. And so we see that with the 2p sub z orbital. We'll also see that if it's a p sub y orbital, because there's 3 atomic orbitals, p sub x, p sub y, and p sub z. And this means that I can make, let me erase that really quick. I can create 2 pi bonds, or 2 pairs of pi bonds, one being bonding, one being anti-bonding, for the p sub z and the p sub y. And we're going to see how the energetics, of these molecular orbitals, regardless if it's a sigma bond or a pi bond, depending on whether it comes from an s orbital or a p orbital, how they align up energetically with respect to one another. The way we're going to do that is to start with a very simple molecular orbital diagram. Now, before I continue on to that, I have a page of notes that I want to cover. All right, this is going to summarize the information that we just talked about. Sigma bonds can be formed between either 2 s orbitals or 2 p orbitals that are end on end to one another. Okay, sigma bonds have no nodes that cross the 2 nuclei ever. Pi bonds can be formed between 2 p orbitals that are parallel to one another, and it will always have one node that intersects the 2 nuclei between those 2 atoms. Principal quantum number energy values are obeyed, meaning the sigma bond that's created from 1s orbitals will be lower in energy than a sigma bond that is created from 2s orbitals, and so on. All anti-bonding molecular orbitals have a node that separates the 2 atoms and will have different phases. Remember, we're looking at deconstructive interference, which is why we don't make a molecular orbital. In general, the formed bonding orbital will be lower in energy than the original atomic orbital, and the anti-bonding orbital will be higher in energy than the original atomic orbital. In general, and the reason I'm saying in general is next semester in Chem 401, we're going to learn about how metals make molecular orbitals with their d orbitals. Remember that the atomic orbitals that a vanadium atom has is all the 5d orbitals. dxy, dxz, dyz, dx squared minus y squared, and dz squared. When I bond atoms around a transition metal, depending how they're bonded around that transition metal, some of those atomic orbitals will actually not make molecular orbitals at all. And that's something that you'll discuss in Chem 401. We will put together MOs in a molecular orbital diagram to give us the full bonding picture of the molecule. And I'm going to write this at the bottom. I'll probably say this again. The general skeleton of the MO will be given on the exam. So you don't have to draw these diagrams from scratch. You will be given basically an outline that you have to fill in. All right. So what I'd like to do for the remainder of this time, I don't know how much time we have left. Let me check. We have, 33 minutes, so 50 minutes, roughly. We're going to complete the MO for several molecules. We're going to start with hydrogen, which is just H2. Oh, looks like my dog just left. Bye, Sammy. We're going to look at some more complex molecules like dilithium. We're going to look at oxygen gas, nitrogen gas. These are molecules that have their own MO diagrams, and we're going to fill in electrons. So let's start with the simplest molecular orbital diagram, which corresponds to hydrogen. All right. So the following figure shows the energy levels for the atomic orbitals, all the molecular orbitals, whether they're bonding or anti-bonding, then the location of all electrons in the molecule. And this is going to be important for us because it's going to give us the discrete information as to how the bond between the two atoms are to be. The number of molecular orbitals in the middle of the diagram. And it's important to note that for this note here, remember, law of conservation of mass and energy says that I cannot destroy or create matter, right? This is also true for energy. I cannot create or destroy energy, I can only transfer it. I'm going to put a big old star next to this because this is important. The number of molecular orbitals in the middle of the diagram will always be equal to the number of atomic orbitals in the diagram overall. MO diagrams must obey all quantum number rules. This is Aufbau, Hans, Pauli. We're not going to be breaking these rules. They still apply here. The blank MO of the diagram will always be given to you on the exam for free response questions. So here is the blank diagram for hydrogen. And we have a y-axis which corresponds to the energy of each atomic orbital and molecular orbital. We have a set of lines that are connected to one another. I'm going to use two different colors here. All right. I'm going to use, let's say, orange or red-orange to describe the molecular orbitals. And I'm going to use, let's say, green to describe the atomic orbitals. So atomic orbital or orbitals. Atomic orbital orbitals. Because we can have more than just one atomic orbital for a specific atom. Oxygen has not only s orbitals, it has p orbitals. We have to describe that in our diagram, right? Now, sometimes what I will give you is the specific, what each line corresponds to. This is for hydrogen gas, or just the hydrogen molecule. This is two hydrogen atoms that are bonded together with a single bond. The two lines on the left and the right correspond to the individual hydrogen atoms before they make the bond. And the way I describe that on this diagram, I'm going to move this out of the way so I have some space. In fact, let's just draw an arrow here. Let's move this. In fact, let's just move it down below. Yeah, there we go. And then I will draw a little arrow. Okay. The way we describe this to the reader is by saying, hey, this line on the left corresponds to the first hydrogen atom. This line on the right corresponds to the second hydrogen atom. The lines in the middle correspond to the molecular orbitals for the molecule H2. Sometimes I will give you this info. I'll say, hey, this is this atom, this is that atom, here's the molecule. Sometimes I don't give you, which means you have to be able to discern that information on your own. When I fill this diagram, I have to fill in specific pieces of information. I have to fill in the identity potentially of each atomic orbital, or sorry, the atoms themselves. I have to fill in the specific atomic orbital for that element and the specific molecular orbitals. And in fact, on the next page, I actually have instructions for how to finish this question. The lines on the left and the right of the middle portion of the diagram are atomic orbitals. For hydrogen, hydrogen only has a 1s orbital. So I'm going to denote that by literally writing that this line corresponds to a 1s orbital and this line corresponds to a 1s orbital. Okay. The middle portion corresponds to H2. Now, in order for me to determine whether the middle portion is a sigma bond or a pi bond, you have to think about how the atomic orbitals overlap with one another. If I go back a few pages, the only type of molecular orbital I can make when I take two s orbitals and allow them to make the pair of molecular orbital is a sigma bond. So the line on the bottom is going to correspond to a sigma bond. And I'm going to literally correspond that with the Greek letter sigma, so that the reader knows that that line corresponds to the molecular orbital. Now, this is a bonding molecular orbital because it's lower in energy than the original atomic orbital. So I'm not going to write a star here. That's wrong, because a star corresponds to an antibond. This is a bonding MO. But what I have to tell the reader is, that's all fine and dandy that this is a sigma bond. Where does it come from? Where are you making this from? What are the original components, the original Lego blocks that made this molecular orbital? Well, it came from a 1s orbital. The way we discern that is by just following this dashed line. The dashed line that connects the bottom line comes from 1s. So I'm going to tell the reader that this is a sigma 1s molecular orbital. The line at the top corresponds to that anti-bonding MO. This is the destructive interference that is higher in energy. So to tell the reader that, I'm going to, again, write sigma, but I'm going to write a little star in 1s. So now the reader knows that that antibond comes from the 1s atomic orbitals. And that's something that we would see in, wrong page. Here we go. In the instructions for how to fill this out. So what I'd like to do here, my dogs are barking at something. Probably hear a bike or something. The last piece of information that I have to fill out for this diagram to complete the picture and get all of my points is electrons. Because I have to fill the diagram with electrons. And what's important about that is, in a little bit, we're going to talk about bond order again. In section 8, I stated that bond order is simply 1, 2, or 3, where a 1 corresponds to a single bond, a 2 corresponds to a double bond, a 3 corresponds to a triple bond. We're actually going to be able to quantify bond order a little bit more efficiently here. And it's going to allow us to introduce fractional values for bond order, okay? What I'm going to do first is fill in the number of electrons that a hydrogen atom has by itself. All right. A hydrogen atom has just one electron in its atomic orbital, and I'm going to correspond that with a upspin electron. This is also true for the other atom as well. Due to the law of conservation of mass and energy, however many number of electrons I begin with, the middle portion will have that same number of electrons. And when I fill in this middle portion that corresponds to the molecular orbitals, I'm going to obey the Aufbau, Hund's rule, and Pauli exclusion principle. So from low energy to high energy, I'm going to maximize my spin, and no two electrons can have the same quantum number set. So because I have 2 total electrons to play with, I only have 2 electrons to put in this molecular orbital. And the way I do so is 1 spin up, 1 spin down. And this is the complete diagram. We're done. If you fill in the diagram like such in a free response question on the final exam, this will get you all the points for that portion of the question. The last thing that I want to talk about here, though, is bond order. Because I can calculate the bond order for a hydrogen molecule. So I'm going to draw the Lewis structure of hydrogen. It's just HH. And we know that the bond order is 1 because this is a single bond. But here's something really nice. Bond order has an equation associated with it. It is equal to the number of electrons in bonding MOs minus the number of electrons in anti-bonding MOs, all divided by 2. And something really interesting happens when I use this equation based on the diagram that I have in the previous page. Now, the number of electrons is with regards to the electrons in this portion of the diagram. Let me change this to red-orange, okay? So we're not confusing ourselves. Okay. The number of bonding electrons in hydrogen is 2. The number of anti-bonding electrons is 0. So the bond order for H2 is equal to 2 minus 0 over 2, which is equal to 1, which is the same exact number as our definition that we covered in section 8. That is really convenient. It just so happens that whenever you use this equation, you will get the same exact number that agrees with the Lewis structure. That's really nice and convenient. But it also allows us to have bond orders, values that are fractional. We're going to see that with our next example. Okay? And molecular orbital diagrams not only give us the ability to get fractional bond orders, but it also tells us exactly why certain molecules cannot be made. And the example that I'm going to cover is dihelium. Helium is a noble gas. It does not create a molecule. We know this. It doesn't create any molecules at all because it's unreactive. The molecular orbital diagram is going to give us that information very conveniently. So let's split this up. I have two MOs here. The top diagram is going to be the MO for helium, just dihelium, He2. And we're going to see here that it is not possible to make a molecule that is He2. But not coincidentally, but surprisingly, it is possible to make this molecule, and we'll see why in a second. Because if the bond order for any two atoms is 0, then you didn't make a bond. There is no bond between those two atoms. And the way that happens is if the molecular orbital diagram is completely filled, meaning I have 2 electrons here and 2 electrons at the top, everything cancels itself out. And what we're left with is just atomic orbitals. So just like with the previous diagram, helium, and I'll use the same colors again. So green for the atomic orbitals and dark red-orange for the molecular orbitals. Helium only has a 1s orbital. It's in the same row as hydrogen. And we're going to say that this line corresponds to this helium atom, this corresponds to that helium atom, and this line corresponds to He2. All right. This line corresponds to the sigma bond that's created between two 1s orbitals, and this line corresponds to 1s star, the antibond from those two 1s orbitals. You could put the notation for the molecular orbital to the side here, and I would give you credit. The number of electrons that helium has is 2. There's 1 spin up, 1 spin down, 1 spin up, 1 spin down. And I just realized that I wanted to use dark orange. I'm lying to you guys. I'm sorry. So He2, this is sigma 1s, this is sigma 1s star. I have 4 total electrons to play with. 2 from the right helium, 2 from the left helium. And when I fill those electrons in, 1, 2, 3, 4, we see the bond order for He2 is equal to 2 minus 2 over 2, which is 0. Which means there is no bond between 2 helium atoms. It is not possible for that to happen. But if I strip just 1 electron, 1 singular electron from one of these helium atoms, all right? So let's go down to the bottom diagram here. Again, this is 1s, this is 1s, this is sigma 1s, sigma star 1s. The lines on the left and the right, we're going to say this corresponds to a helium atom. This line is going to correspond to a helium plus because the molecule is He2 plus. I've lost 1 electron. Again, Dr. Ochoa, use red. Like, what are you doing? He2 plus. Okay. The number of electrons that the left helium has is 2. But the right one only has 1. So when I fill my diagram, now I have 3 electrons to play with. 1, 2, 3. So the bond order, let me give myself a little bit more space here. The bond order for He2 plus is equal to 2 in the bonding MOs minus 1 in the anti-bonding MO divided by 2, which is equal to a half, or 0.5. That means if someone were able to, and as far as I'm concerned, I don't think anybody's done this. If someone were able to create this molecule, He2 plus, and trap it and prove to somebody that they made it, the bond between those two helium atoms is kind of a single bond, but not entirely a single bond. It's kind of like in between being a bond and not being a bond. But they are technically bonded. It's just that bond is really, really, really weak. So you can't technically make this molecule. All right. At this point, I would say, are there any questions? Obviously, you'd have to email me or come to office hours to answer those. So we're going to keep going. Let's do something a little bit more complex. Let's look at dilithium. Complete the MO diagram for the molecule dilithium, Li2. Include the names of all atomic orbitals, molecular orbitals, correct number of electrons, and the identity of each atom and molecule at the bottom of the diagram. So if I were to write down the electron configuration for lithium, lithium is 1s2, 2s, 2s1. All right. So I actually have some 2s orbitals to deal with. And the way I'm going to describe the diagram for that looks like a stacked version of the hydrogen diagram, okay? Where the bottom portion of the diagram corresponds to all the bonding and antibonding orbitals that are made from the 1s orbitals, and the top portion corresponds to the 2s orbitals, along with their corresponding antibonding and molecular MOs. So I have two lithium atoms. Let's write that down. We have a lithium atom on the left, a lithium atom on the right. Let me rewrite this L because that looks ugly. And then the middle is going to be Li2. The lines at the bottom correspond to the 1s orbitals. The lines at the top correspond, apologies, to the 2s orbitals. The lines in the middle are still going to correspond to sigma bonds, but the identity of where those sigma bonds come from are different. So for the bottom half of the diagram, this sigma bond comes from the 1s orbital set. This sigma star, the antibond, comes from the 1s orbital set. The top portion is still a sigma bond, but it comes from a 2s orbital pair. And this comes from a 2s orbital pair. And it's an antibond. Now, what this diagram is essentially showing you is, remember that the noble gas configuration for lithium is helium 2s1, where these are core electrons and these are valence electrons. Our diagram shows exactly the same information, where this part of the diagram is the core electrons, and this part of the diagram are the valence electrons. And something interesting happens to this diagram when I fill it out. Remember I said core electrons do not make bonds. They just chill out. The reason I told you is because they're too low in energy. They don't want to make bonds because they're already low in energy. They can't make any bonds from that low energy state. We actually see that not only are they low in energy, but when I fill my molecular orbital diagram, all of the electrons that comprise the molecular orbitals for the bottom half of the portion cancel each other out. Let's see that. So I have 2 electrons here, 1 electron for that lithium atom, 2 electrons here, 1 electron for that lithium atom. The total number of electrons that I have to play with is 1, 2, 3, 4, 5, 6. So I have 6 total electrons that I can fill the internal portion of my diagram. So when I do that, it's 1, 2, 3, 4, 5, 6. When I do the bond order calculation, let's do that on the next page really quick. The bond order for dilithium is equal to, let's scroll up here, 1, 2, 3, 4 number of electrons that are bonding MOs minus 2 in the anti-bonding MO divided by 2, which is equal to 1. Now here's something interesting. I'm going to put a little star here and say using only valence portion. I'm going to calculate the bond order of dilithium, but only looking at this portion of the diagram, not this portion. I'm ignoring the electrons that are down here. Well, then that's going to be 2 minus 0 divided by 2. 2 minus 0 divided by 2, which is equal to 1. Ah, they're the same number. Which, because of this fact, and this is true regardless of whatever molecule you do, on an exam, you will almost always have to fill the valence portion only, because the core electron portion of this diagram cancels out every single time. Let me take a look at how much time I have. We have about 25 minutes. Fantastic. Let's keep going. So what I'd like to do here, so we've seen how to fill our diagram from atomic orbitals to molecular orbitals, whether the molecular orbital is bonding MO or anti-bonding MO. We're going to look at molecular orbital diagrams that have pi bonds. This is the atom has access to more than just s orbitals. And the first molecule we're going to look at is nitrogen. That is N2. So on the next example, here's the skeleton. It looks pretty much the same as hydrogen, except we've introduced a few more lines here. Okay. Now, let me zoom in on this. The electron configuration for nitrogen, the entire configuration, is 1s2, 2s2, 2p, let me look at my periodic table, 3. The noble gas configuration is helium, 2s2, 2p3. So this diagram only shows us the valence electrons because I'm totally missing the part of the diagram that corresponds to the 1s atomic orbitals and the corresponding bonding and anti-bonding MOs. I just didn't include them at all. All right. Now, additionally, I'm going to see that when I fill this diagram up completely, the bond order of this molecule should be exactly the same as the bond order for the Lewis structure. The Lewis structure for, and I'll draw that to the side here, let's say in the top right of this diagram, the Lewis structure for nitrogen is a triple bond, which means the bond order via Lewis theory is 3. It's the number 3 because there's 3 bonds. We should see that when I calculate bond order, when I fill this diagram, I better get the same answer. Otherwise, I've done something wrong. I've done goof somewhere. All right. So let's start filling this out. First off, let's fill out the atomic orbitals for both the nitrogen atoms. We have one nitrogen atom in the left. We have one nitrogen atom on the right. And then the middle corresponds to the molecule N2. Because I'm only filling in the valence electrons, I'm not interested in the core electrons. These lines correspond to the 2s orbitals, and these lines correspond to 2p. There's 3 lines because one corresponds to p sub x, p sub y, p sub z. And because these all have the same energy, they all have the same energy level that is corresponding to this part of the diagram over here. All right, we're all doing pretty good. Let's look at our molecular orbitals. The bottom portion should be fairly simple. There's 2 s orbitals. Those 2 s orbitals can only make sigma. So this is going to be sigma 2s, sigma 2s star. Things are going to be a little bit more complicated for the 2p orbitals. Because if I go back a few pages, our p orbitals can make a sigma bond if they're end on end, whether it's a sigma bonding MO or a sigma anti-bonding MO. If they're parallel to one another, like the 2p sub z and the 2p sub y orbitals, then we can make this pi bond pair and this pi bond pair. If I go back to the diagram, that's signified by these lines. This line corresponds to the bonding MO for when the 2p orbitals are end on one another, and this line corresponds to when they're end on one another, but they're out of phase. So I'm going to signify that by saying this is a sigma 2p, this is a sigma 2p star. The 2 lines that are parallel to one another correspond to the pi bonds that can be made from the p sub z and the p sub y atomic orbitals. So I'm going to write that down as pi 2p and pi 2p star. So even filling this out on your test will get you so many points. So now, let's fill our electrons. The number of electrons I have for nitrogen in the valence set is 2 in the 2s orbitals and 3 in the p orbitals. So I'll have 1, 2, 1, 2, 3. Remember, we have to obey Hund's rule. We always write down our spins in one direction first before the opposite. 1, 2, 1, 2, 3. So let's fill in the middle of the diagram. I just realized that I forgot my lone pairs for this. I know somebody probably would have raised their hand and been like, Dr. O, you forgot the lone pairs on the nitrogen molecule. Okay. The total number of electrons I have to play with is 2 plus 3, which is 5, and 2 plus 3, which is 5 on this side. 5 plus 5 is equal to 10. So I have to fill the middle portion with 10 electrons. Let's do that. 1, 2, 3, 4. I have to obey Hund's rule for this next section. 5, 6, 7, 8, 9, 10. So when I calculate bond order for N2 is equal to the number of electrons in the bonding MOs. That's going to be 2, 4, 6, 8. So that's going to be 8 minus the number of electrons in anti-bonding MOs, which is just 2. There's 2 electrons in the sigma 2s star antibond. 8 minus 2, all divided by 2, we get 8 minus 2 is 6. 6 divided by 2 is 3. Good. That agrees with our Lewis structure. Now, some of you who are a little bit more clever notice that, wait a second, Dr. O, this is completely filled, right? I could just ignore this part of the diagram when calculating bond order. Yeah, you could. You could just calculate this portion because everything here is going to cancel each other out. If I would have done it that way, it's going to be 6 minus 0 divided by 2, which again gives you 3. You're done. Now, I want to do another example. We're going to go from dinitrogen to dioxygen, so O2. Okay, the diagram is going to look very, very similar. Okay, there is a little bit of a difference in the diagram that I'm going to talk about after we filled out the diagram for O2. For now, let's just look at the diagram and fill it out. All right. If you want to take some time to do it on your own, You can pause this video, take a tackle at it, all right? Pause it and try to do O2 on your own. Draw the Lewis structure. Okay, the Lewis structure has a double bond, so I should have a bond order of 2. Fill in all the atomic orbitals, fill in all the molecular orbitals, fill in your electrons, and see what you get. So, pause now, give yourself some time to do it, and then come back and see if you get the same answer I do. So I'll give you some time if you want to do it that way. If you don't want to pause and you just want to watch me do it, let's do that right now. Complete the MO diagram for O2. Include the names of all atomic orbitals, molecular orbitals, correct number of electrons, and the identity of each atom. Okay, so this is O2. So let's firstly, let's write down the electron configuration. Let's just write down the noble gas configuration. Helium, 2s2, 2p4. It's right next to nitrogen. And the Lewis structure of dioxygen is a double bond. So the bond order should be 2. All right, we're doing pretty good. I have 1 oxygen in the left, 1 oxygen in the right. The middle corresponds to O2. Okay. This corresponds to 2s orbitals. And this corresponds to 2p. I forgot I was going to use orange for the molecular orbital portion. The line at the bottom corresponds to the sigma bond that's formed from 2s orbitals. So we're going to say sigma 2s. The top line corresponds to sigma 2s star. Here we have a sigma bond that is formed between 2 p orbitals that are end on end. And here is the molecular orbital, the bonding MO that's created when the p orbitals are parallel. So we have sigma 2p, pi 2p, pi 2p star, and sigma star 2p. We're doing good. The last thing I have to do here is fill my electrons. Before I do that, let me check my time. We have about 13 minutes. So I need to make sure that in fact, I'm probably going to start a timer on my desktop just so that, or on my cell phone, so I don't overshoot that by accident. Nope. A timer. All right. So let's fill our electrons in. Oxygen by itself as an atom has 2 electrons in the 2s orbital, and then 4 electrons in the 2p orbital. So I have 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. All right. Going back down to the molecular orbital levels, I have, let's see, how many electrons do I have to play with? 1, 2, 3, 4, 5, 6. So 6 times 2, because I have 6 on each side, 12. I have 12 total electrons to play with. So, all right, let's fill that out. 1, 2, 3, 4, 5, 6, 7, to obey Hund's rule here, 8, 9, 10, 11, 12. All right. Let's calculate bond order. That's the last thing we have to do. Bond order for O2. The number of electrons in bonding MOs is 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8. The number of electrons in anti-bonding MOs is 1, 2, 3, 4. So that's going to be 8 minus 4 divided by 2, which gives me 2. Fantastic. It agrees with the Lewis structure, which has a bond order of 2. Again, I drew it right here. So our bond order from the molecular orbital diagram also agrees with the bond order from the Lewis structure. Now, before I continue, because I do want to talk about, some of you probably already noticed the difference between this diagram and the previous diagram, which is, if you look at the level here, it goes I have two p orbitals that make the pi bonds. Then I have the sigma bond from the two p orbitals, and then I have the antibond equivalent. So the order of the levels is two that are the same level, one, two, then one. If I look at the oxygen diagram, though, it goes 1, 2, 2, 1. There's a difference here, and there's a reason for that I want to talk about in the next slide. But before I get to that, there's one more thing that I want to talk about. In section 7, when we introduce electron configurations, we introduce the idea of paramagnetic and diamagnetic. A paramagnetic species has unpaired electrons in its electron configuration. A diamagnetic species has all of the electrons are paired up. We can actually see exactly the same thing for molecular orbital diagrams. So let me just write the definition here just to refresh you. All right, let's use blue. Paramagnetic let's just say there are unpaired electrons in electron config or in the MO. Diamagnetic let's say all electrons are paired in electron config or MO. Now, when we're trying to figure out whether a molecule is paramagnetic or diamagnetic, we're going to use the molecular orbital diagram, and we're specifically only looking at the part of the diagram that corresponds to the molecular orbital. I'm only interested in the electrons that are in this portion to determine whether the molecule is magnetic or not magnetic, meaning it aligns itself with a magnetic field or it doesn't align itself with a magnetic field. You'll notice that for nitrogen, for N2, all of the electrons in the MO portion are all paired up, which means, and I'll put this in blue down here, N2 is diamagnetic because all the electrons are paired up in the MO portion. I know that some of you are probably like, wait, Dr. O, these electrons are unpaired. The electrons are unpaired if it's a singular nitrogen atom. That's true. But now the nitrogen atoms are bonded together. All right. For oxygen, I have two electrons that are unpaired at the very top of this diagram, which means O2 is paramagnetic. And it only takes one unpaired electron in my MO to make that molecule paramagnetic, meaning if I put it in a magnetic field, it will align itself with the field. Now, some of you, I heard licking and I was like, what the hell is that? It's my dog. He's under the desk. Sammy, are you okay? Okay. I know it's hard to visualize the idea of oxygen lining up with a magnet. Like if I hold a magnet up in just air, we don't it's impossible to see those oxygen molecules like sticking to the magnet, right? There is a way we can actually see this. I will look online to see if I can find a video of it. When I used to teach at UC Davis as a lecturer, this was actually a demo that I would do for students. If you make liquid oxygen, which you can, you just take gaseous oxygen and you lower the temperature till it turns into a liquid, and you pour that liquid oxygen over a magnet, it'll stick to the magnet. That's because all those oxygen molecules are magnetic. They're paramagnetic, meaning they align themselves to the magnetic field of the magnet. I should state that it's not that the molecule is magnetic, it's that it's paramagnetic, so it aligns with that magnetic field, okay? Nitrogen, liquid nitrogen, again, if I go to the diagram for nitrogen, This is a diamagnetic molecule, which means it shouldn't align itself with a magnetic field. And sure enough, if I take liquid nitrogen and I pour it over a magnet, none of it will stick. It'll just go right through because it's a diamagnetic molecule. So that's the type of question you may get on the final exam. All right. Now, if you wanted to, you could stop here and play around with these diagrams. You can draw one for yourself and maybe play around with the molecule. Maybe make this N plus so that this is N2 plus and see what happens to the diagram. And of course, the homework has questions like that as well. We're going to continue on though because we have about 5 minutes. Let's talk about what happens to these energy levels. Why do they change? The reason they change is because of a specific phenomenon. It's called sp mixing. What is sp mixing? Sp mixing occurs when the s and p orbitals have similar energies. When a single p orbital contains a pair of electrons, the act of pairing the electrons raises the energy of the orbital. Thus, the two p orbitals for oxygen, fluorine, and neon will be higher than the energy levels for the two p orbitals for lithium, beryllium, boron, carbon, and nitrogen. Now, what happens is because the p and s orbitals have a different energy level, this results in an energy change for the molecular orbitals. And so what we see, here I have a diagram displaying this. For molecules that are diboron, 2 carbon atoms, 2 nitrogens that are bonded to each other, the energy level will always be 2, 1, 2, 1. I'll actually write that down with my marker. 2, 1, 2, 1. For molecules that are O2, F2, or Ne2, the level is different because of that sp mixing. So here we have 1, 2, 2, 1. Regardless of whether the molecule is ionized, meaning if I have C2 plus or C2 minus, the level is still 2, 1, 2, 1. It doesn't change it. And if I have O2 plus, then the level is still 1, 2, 2, 1. You will have to memorize this order. I know that I'm going to give you the skeleton of the diagram, so you don't have to draw the white portion of the diagram on your own. But potentially I might give you a question that says, hey, for the sigma and the pi orbitals that come from the two p's, what is the energy level? Is it 2, 1, 2, 1 for this specific molecule or 1, 2, 2, 1 for this specific molecule? So you'll have to memorize that. I have another diagram that shows that we have an increase of S and P mixing as I go to the left for boron, carbon, and nitrogen because the energy levels change as I get closer to oxygen, fluorine, and nitrogen. And we see that the levels increase. It's an inverse proportional to the size of the atom because remember that as I go from the left to the right, the atom gets smaller. And as it gets smaller, those core electrons go lower in energy and resulting the valence electrons also are affected by that. We have about 2 minutes left, so I want to keep going here. We're done with molecular orbital theory. Okay. But what we have to do here is molecular orbital theory, again, is really, really good at describing all types of bonding, whether it's a linear molecule, trigonal planar, octahedral, you name it. But remember that for more complex molecules, the math gets really nasty really fast. So what we're going to do here for the very last thing we're going to talk about, and this is going to be really important for organic chemistry if you're going to take it, we're going to shortcut it. We're going to shortcut our method here by introducing what we call hybridization theory. Hybridization theory is going to take molecular orbital theory and kind of cut out the fluff out of it. It's going to allow us to describe quantitatively the energy level for molecular orbitals that are created for really weird bond angles, like tetrahedral molecules that have a bond angle of 109.5. All right. So it's going to simplify it, but it's not going to simplify it to a point where we're not able to describe the quantifiable energy level for the molecular orbital that's created from the atomic orbitals. What is hybridization, though? It is a mathematical procedure. So for molecular orbitals, I Took my atomic orbitals and I added them together, right? I got them MO. Hybridization does the same thing. It's a mathematical procedure in which the standard atomic orbitals are combined, they're added together to create hybrid orbitals. A hybrid orbital is the literal addition of, let's say, an s orbital and a p orbital. What does it look like? Hybrid orbitals are formed from the combination of standard atomic orbitals that correspond closely to the actual distribution of electrons in a chemically bonded atom. So what does that look like? This is the last thing I'm going to talk about before I let you go. If I take an s orbital and I take a p orbital, I can take these atomic orbitals and allow them to add to one another. Okay, this is just another way to look at bonds between two atoms. It's another theory that allows us to describe the bond between two atoms. And it's going to allow us to describe with very good efficiency and information why certain organic molecules look the way they look. And it's important for organic chemistry and biochemistry and anything with regards to proteins, because proteins have a bad tendency of folding on one another, ways they're not supposed to fold it. In fact, the folding of proteins is actually important for why I was in the hospital, which we can talk about on Wednesday if I have enough time. All right. If I take that s orbital and that p orbital and I add them to one another, you'll notice that this part of the p orbital is phased blue, let's say, and the s orbital is phased blue. They add to one another to make this weird oblong asymmetric dumbbell. And this dumbbell is the hybrid orbital. And that's what we're going to talk about on Wednesday. So we have some notes for hybridization. This will be the last thing. The number of standard... In fact, no. Let's stop on the previous slide. We'll stop here. On Wednesday, we'll finish the very last portion of the notes for the semester, and that will be that. Thank you again for watching. I apologize that I was not able to make it to class on Wednesday last week, and that circumstances have led that this lecture has been recorded online, but I do hope that nothing changes and I'm able to see you on Wednesday. All right.